Molar enthalpy of formation. Elements are used as the zero reference point for energy. That doesn't mean that when you have an O2 molecule, there isn't any chemical energy stored in that covalent bond between the two oxygen molecules. But when we use energy, we're typically not looking at absolutes. We're not interested in how much absolute energy there is in something. But instead, we're interested in changes in energy. When there's a change in energy, be it positive or negative, it means that that energy will be available to the environment in other forms. So we're not concerned about exactly how much chemical energy something has. We're just interested when it goes through a reaction, how the amount of chemical energy it has changes. It's kind of like this. If I drop a ball from a height of 2 meters to the floor, and that ball falls through the 2 meters to hit the floor, I don't really care if I did this experiment on the second floor of this building or the first floor of this building. See, we're in a school right now, and so I could have been standing up here on the second floor where we happen to have our physics lab and dropped that 2-meter ball, or it could have been standing on the first floor and dropped that ball from 2 meters. The speed it hits the ground at is going to be the same, because in the end, it's not important if I call this height 0 or this height 0, and if it drops from 2 to 0, going through a height change of 2 meters, or if I call this height 0, and I say here it was up at 12 meters and only dropped to 10 meters, see, this would have been 12 meters, and this would be 10 meters. It's still only dropping through 2 meters of change. And so the amount of speed or the amount of energy that's available for speed is the same regardless of where I set this reference point. So in the end, because I'm not interested in the absolute value, I'm interested in the change, we can make 0 wherever we want to make it. For chemicals, we're just looking for something consistent. So the most obvious consistent thing is the atom's elemental form. What that means then is if we want to define the chemical potential energy associated with any compound, we should naturally compare it to the chemical potential energy of that same compound in its elemental form. Let's take methane as an example, CH4. Methane, if it was going to be made from elements, would have to be made from CH2, carbon and hydrogen. For every 1 carbon, we'd want 2 diatomic hydrogens, leaving us with our CH4. If we call this 0 energy and this 0 energy, then we can define the potential energy associated with that methane as, and this is just off of a chart, negative 74.4 kilojoules. That doesn't mean that if we were to do absolute energy, that methane would sit at negative 74.4. What it means is wherever we had our elements, methane is 74.4 below that. We call this the molar enthalpy of formation, as we consider it to be the thing being formed from its elements. So this absolute scale doesn't really matter if all I'm interested in changes. So what's much easier than trying to figure out what this is or that is to say, well, let's just reset it so that this is 0 now. And then we can compare changes from that 0 line for any type of material. So once again, where we set our 0 point is arbitrary because we're interested in change. We're not interested in absolute amount. Since we can do that, we set elements as 0. And if we set elements as 0, then the energy associated with any compound, any combination of elements, makes sense to simply compare them to their elements by doing the molar enthalpy of formation, which is the amount of energy, in this case released, but either released or gained, when a compound is formed from its elemental form. One quick note here, elemental form. Yeah. One quick note here. Because I'm not interested in the elements really in a meaningful way here, I'm focused only on the compound that's being created. Unlike usual, I'm free to use fractional coefficients as needed to make sure that I can make 1 mole of my product when defining this delta H. In that way, when I do it, I'm always getting the amount of energy per 1 mole of that specific substance. So that's how we represent the molar enthalpy, or the change in kinetic or chemical potential energy for compounds.